Derivatives of other trig functions. So then first one they're going to talk about is derivative of tan. X is secant squared x. That proof is just right here for you. In order to do this derivative, you're going to write tangent in the form of sine over cos. Do quotient rule. So low d high. So derivative of, d high, d of x, minus high d low, all over low squared. Derivative of sine is cosine, so now you have a cos squared. Right here is a negative sign. Now you have a positive sine squared. And then you get that cool little cos squared plus sine squared is 1. So that's cool. And then you have 1 over cos squared, which is secant squared, because secant is 1 over cos. Okay? I would just say in general, if you don't know that cosecant's 1 over sine and that cosecant's or secant's 1 over cosine, you're going to get that down. That's kind of assume that you know that. Okay? So if you need help with that, just let me know. Okay, next one, the derivative of cosecant is a little bit different. It's negative cosecant x cotan x. Again, you don't have to memorize these. On that formula sheet I gave you yesterday, they're all on there. It's in the trig section. Okay, so even when I put this box up, I'll kind of show them to you. You can write them down in your notes if you want to, but again, it's on the formula sheet. You can just highlight them if you'd like. Okay, so proof of this one, again, cosecant's 1 over sine. So then we're going to do the derivative of that, which is sine to the negative 1. So you drop the negative. Now it's a negative 2. And so then, don't forget, though, you have to derive the inside as well. That's what they're doing here, chain rule. And so then there's a cos x here. So then you have negative 1 over sine squared x, which is your, you could write this, everybody asks me, why can I write this as negative cosecant squared? Because they like to write it with all cosecant cotangent so that it's on one line. So that they do is they go ahead and take one of these out, one of the sine x's out, and they put it under the cosine to get the cotangent, and then they leave this as cosecant. That way we don't have to have any squares. So they kind of did it to get rid of squares. So what I'm telling you is that yes, I've been asked this last year before, this is technically negative cosecant squared x, cosine x, but they wanted to keep it without squares. So what they did is they went ahead and wrote this guy, this square, twice, like that, and they slid the cosine x to the top. That now is cotangent, and that is just cosecant. That's what they did. Okay, again, the proofs aren't super important other than getting used to, like getting used to what 1 over sine x is, or cosine over sine x is, stuff like that. So here's all your derivatives of your trig functions that you'll be using for this section. Like I said, we're probably going to finish this section this week, so you probably have, either we can talk about it, we can vote, we either have a quiz next week on it, or we can make it like a unit test that's worth half. Less stuff means less stuff, so that might be helpful, but we can put it wherever you feel you think's best. So you got derivative of sine's cos, derivative of cosine's negative sine, derivative of tangent secant squared. Derivative of cotangent is negative cosecant squared. So the only change there is it's a negative with the flip. Secant x is secant tan x. Cosecant x is negative cosecant cotan x. Okay. Like I said, you don't have to write all these down. You can if you want. They're in your formula sheet. So I'm just going to try to go quickly so we got a short period. All right, so let's find the derivative of this right here. So we want to find f prime of 1 over 1 plus tan x. So first of all, especially when there's not anything on the top, like automatically, some of you guys aren't doing this, and you didn't do this in your test either, you need to think about pushing it up. It's so much easier to write it like this. Some of you guys try to quotient rule that, and there's no reason to do that because the top's a constant. The top's a constant, your quotient rule is kind of irrelevant. You want to use quotient rule or product rule when you have two variables or two, I don't want to say things, but that's kind of the only thing I think about to explain it. When you have two things, like that's just a 1. Derivative of 1 is 0. Okay? So if I write it like this, I drop the negative. I go 1 plus tan x in here. The derivative of the inside, well, the 1's nothing. What's derivative of tan? We just on our sheet there. Derivative of tan, all these memorized. Secant squared x. Okay, and then since we dropped the negative 1 down, remember that makes that negative 2, and we're done. F prime of x is, you can put the negative out on the side, whatever you want to put it, doesn't really matter. That's the derivative. Any questions with that? Okay, I'll let you try example 2. Okay, I'll pause the video so you can have a second. I'll take attendance. Okay, go ahead and try this one. All right, so with this one we have our chain we have to do from the inside portion there. These are just a simple x. So the first thing when I see these ones, especially with this little right here, that 3, just kind of, I wouldn't say confuses me, but I just like to see it better like that. Because that's what it means, right? The whole thing is cubed. So just you can kind of see what you're doing a little bit easier. So in terms of this one, there is no like product rule. Hope you didn't try to do anything like that. Okay, you just drop the 3. Okay, drop the 3. It's 6 cosecant. You keep what's inside. Then you derive the inside, which is cosecant. What's the derivative of cosecant? Yeah, negative cosecant, cotangent. Now this is where it gets a little tricky. You have to keep the same base, if you will. You have to keep that. It's not just an x. It has to keep that same form. Okay, and then it's also the cotangent. Okay, it's a square there. And then now the derivative of the inside, which is 6x. Just goes in the end there. Okay, so just to write this all as one piece, it's going to be, okay, so you're going to have 6 times 6x, so that's 36x. What else can we do? So the other thing we can do is I still have a cosecant 3x squared and a cosecant 3x squared. I can put that back together, and it's a cube again. I'm writing it like the book's going to have it. Okay, and then you have your cotangent. Negatives out here, yeah. Whoa, whoa, whoa. Those two as in what? Yep, because they're the same base. So it's just like exponents, right? If you have like an x2 times an x, that's just an x cubed. They're the exact same inside. Okay, because this is a 1 here, right? Okay, that makes sense? No? It's fine. Let's talk about it. I'm not going to keep going. Okay, so I'll walk through it again. So again, I rewrote it like this up here to kind of see what I'm doing with the 3 here. I'm dropping the 3 first, just like normal. And then this is where it's chain within a chain. So I have to take derivative of this. I keep the 3x squared for that part. And then I have to take derivative of the 3x squared. Well, the tricky part is the derivative of the cosecant is negative cosecant cotangent based off your definitions on the previous page. They hold the same form as, 3x squared, 3x squared. The derivative of 3x squared is 6x, and that's here. So this was like, that's chain 1. This is chain 2, if you will. Okay, so we're undoing those chains. Now we have all those written out. We're going to put everything together the best we can. 6, this is all multiplied. So you just kind of put stuff together that makes sense. 6x times 6, and then with the negative, is negative 36x. I have a cosecant 3x squared squared and a cosecant 3x squared to the 1. That's like exponents of 2 plus 1, which is 3. And then this guy just stayed the same, and he's by himself. Okay? All right. We have quite a few of them, so. If tan y equals x squared, find the derivative of y with respect to x. So this is our lovely implicit differentiation coming back. Okay. So what happens here is, remember, you're doing implicit, you take the derivative of everything, and every time you have a y, you have a y prime, right? So you're doing it with respect to x. That's why it says respect to x. So the derivative of tangent is what? Secant squared y, right? We keep the y. And then it's y prime. Why is it y prime? Because we do have to do the derivative of the inside, even though it's not like, if it's just an x, you don't have to because it's a 1. But if you do the derivative of the inside, it's 1y prime. That's the part about implicit that's confusing. So let me say that again. Derivative of tan is secant squared y. If this was 2y, we'd have to take the derivative of that and get 2. But it's just derivative of just y, which is just 1, but it has to be 1y prime. Okay, because it's a y, not an x. That's just our implicit. That's times. I'm going to have to get some new pens. Like that. 2x. And so then all we do is we divide the secant squared y over. And this is where it gets interesting. Well, not super interesting. Relax, relax. What is secant squared on the bottom, really? It's cosine squared. It's not derivatives. It's because secant of x is the same thing as 1 over cos x. So if I have secant on the bottom, then that is cos x. Well, the y is part of it, right? The y is the base of it. It's secant of y. Just write it nicer. You can leave it. They're just putting it, they're just kind of like, it's back to that puzzle idea, right? Where, like when we were doing our related rates problem, I always said, figure out what you need and try to figure out how you can get it. The problem here is there's going to be things that you need, and you may not see right at the bat. Could you write something in a different, secant or cosine way that will help get you to where you want to go? It's going to be that kind of game, so don't get set on, like, it's not going to be so black and white all the time. Like, we're going to write these differences just so that you can see that's an opportunity. Because like what happened actually, Ryan, is like a perfect example is they would say, solve this, your answer should be this. And I've seen people pull their hair out because there's like, I got this. I don't know why. How am I going to get cosine? Well, that's why. Those type of things are going to happen. Yeah, so that was his question. And so what I'm saying is that they're always going to, in these examples and in these notes, they're going to make sure that you see all opportunities of how it could be written. Because you don't get fixated on it has to be this or it has to be this. It can be either.
So on a test, is it going to say which way to write it?
It could. That's what I'm saying. On a test, I could say, I want you to tell me how it's this, but you'll do this and probably be like, well, I can't get here. That's the point. You have to see that these are the same. But in a test, if it's open, then you put both, then those are both acceptable. Yeah. Okay, I'm not going to say, no, I wanted that one. Sorry, Tatum. Doesn't work. Okay. All right. Good? Good? All right, so 4, find the slope of the tangent line. Okay, derivative, translation, right? Find the slope of tangent line. Y equals tan cosecant x when sine x equals 1 over pi. On the interval of 0 to pi over 2. Okay. All right, so what we're going to do first is let's do the derivative first, and we'll talk about what that other stuff means. So if we do y prime, we know that tangent's cosecant squared, right? Or secant squared, sorry. Derivative of cosecant, because I do it at the inside, is minus cosecant x cotangent x. Okay, if you're saying, don't we have to keep the same form? Remember, I'm taking the derivative of this, and its form is x. So those kept x's. And this is multiplied, not minus. That whole thing's multiplied, except for this guy's separate. Like, you can't multiply these two because he's linked to the secant squared. Like it's I don't know what it's called to get the wording, but I keep wanting to say base, but I know that's not right.
So it's like a chain rule?
Yep.
You take the derivative of the one and the other.
Yep, it was a chain rule. So derivative of tan is secant squared. We kept that. Then we took the derivative of this, which is this.
Okay. Would you be able to put cosecant at 1?
Yes. I see what you're saying. So like in the beginning?
Well, just because you have the sine.
Yeah, you could. Yeah, you could. Okay. All right, so that's where we're at. And so we want to look at it for when sine of x is 1 over pi. What does that mean? This might have been something we haven't really talked about, but so we need to figure out essentially what is x at that point. And so another way we can write this is if sine of x is 1 over pi, then cosecant x is pi. And now we actually have something there. Because now we know what cosecant x is. Kind of weird, huh? So I tell you sine of x is 1 over pi. So what I did was, that means that cosecant, which is 1 over sine, is pi. And so now we're going to take, we can put the pi here, we can put the pi here. Okay. We also, though, we have a little bit of work to do. We're going to have to use the Pythagorean triple. We want to figure out, we need cosine now, because I have a secant, and I have a cotangent that has a cosine in it. Right? Cotangent's going to be cosine over sine, right? So I need to get a cosine relationship of that. So what I'm saying is that, I'm not sure if you've done this or not, but we do know this, right? Equals 1. And so then when we're relating them to each other, then we go ahead and we say, okay, if I want cosine, it's going to be cos squared x equals 1 minus sine squared x, right? And then we're going to square root it. So that we get what cosine x is. If you're saying, I don't, like, how does it help us? Well, I know what sine x is going to be. And so I can put 1 over pi into that. So we know, they tell us that sine x is 1 over pi. So I just put 1 over pi squared there. Because that's the form that's, again, this is where we're talking about the puzzle type game. Like, this is the relationship we know to relate sine and cosine to each other. Because, okay, back to that. We know what these values are by this, right? This secant squared is 1 over cosine. We don't have a value for cosine right now. We don't know what that means. Same thing here. Cotangent is cos over sine. We don't know what cos is. So those are like my missing pieces. So like if you went and plugged all these things in, you still have some things you didn't know. We're working on filling out the part we don't know. Okay? So when you do that and you plug in the pi, what did I put in there? So 1 squared is 1, pi squared squared. So here, right? I put 1 over pi in here. 1 squared is 1, pi squared is pi squared. That's what cosine is to us.
Because you could put the pi in both the secant, the cosecant.
Yeah.
Secant squared equal to 1 over cos squared x.
Right, and I lied. We're not doing it for this because, well, not yet, because we know what this value is. We can figure out what cosine of pi is. That's not a problem. This is all because of the cotangent. So all I'm saying is that secant squared, we know what's going in here. And so I can figure out what that is. Okay, it's going to be pi. This is the problem. This is why we're doing it.
Well, but you don't have, oh yeah, you do have sine.
Yeah. Okay, So let me put it all in now. Let's just see where we're at. So where we're at is here. Y prime is secant squared of 1 over pi. Or no, pi, excuse me. Because it's cosecant sine. We already said that. Minus minus pi with a multiplication, excuse me, times a negative pi. And then this right here is going to be cos, which is that, over pi. Oh yeah, it's a straight sine, isn't it? Thanks. It's in my notes, just didn't read it. All right, so before I lose everyone, cosecant x we defined is pi because they told us sine of x is 1 over pi. These are reciprocals. Okay, so everywhere there's a cosecant x, we can put pi in here and here. That's why those are there. This is the work we did to get cosine, which we figure out cosine is equivalent to this. And then over sine, and sine is 1 over pi. Okay, so now secant squared is 1 over cosine. Okay, what is cosine of pi? It's -1. Pi is over here. That's -1 for the x value of cosine. But we're squaring it, so it's actually just 1 to us. Okay, so this right here is 1 over cosine, essentially. So we're going to look at cosine of pi. Okay, cosine of pi, pi is right here on the unit circle. That's pi over 2. This is the point, -1, 0. So 1 over -1 is -1, but we're squaring it. So we're back to 1. So this whole thing right here is just a 1. Not the whole thing. This thing right here is just a 1. Too literal. Okay. So then essentially we have to put the pi here. So again, that we're running out of room here. So this is over 1, so the pi goes in the bottom, right? So like in terms of the fractions, if I wrote this guy over 1, I'd have the overachiever, so he goes to the top. So essentially this pi is on the top is what I'm trying to tell you. Okay, so I have another pi on top. So essentially I'm going to have a negative pi. This is a lot longer than I thought it was going to be. Pi squared, and then times the 1 minus 1 over pi squared. And that's where we'll leave it. Because that's a value. What's that? So it's just going to be pi times pi. You can write just pi times pi if you want. Yeah. The denominator. So what I'm seeing is, okay. Are we good? So, but the bottom line is, guys, all the x's are gone. This is a value. So even if you're not quite simplified the same way I am, if you plug in this value, like if you left your pi, if you left it like this even, you'd be fine. Because this is a value. Everything's pi's or numbers. You'll get a number here. Don't think pi is a variable. Pi is 3.14 still. So that whole thing's a value. So we're oversimplifying what you would need to. Just kind of like when you do the derivative, if you don't completely condense it down, you can still find the tangent slope at a point if you plug that value in. It'll still give you the correct answer. Okay?
So where did you, how did you get that pi squared?
This one? These? So cotangent's cosine over sine. cosine we worked out was this.
Yeah.
So that's the top. And then sine is 1 over pi.
No, sorry, just how did you, like, when you got an angle, how did you write that one?
This right here? You don't really have to write that. I just know that this is going to be on the top.
Oh, you just brought it up.
I just moved it over. Okay. All right, actually, we'll stop there, and we'll do the rest of them tomorrow.